In physics, there are two quantities that are generally used to describe how an object is moving. One of them is speed, which I'm going to move down here to the fourth bullet in my slide to start with, is distance over time. Really, it's average speed, though, is defined to be distance over time. It turns out it's easiest to start by presenting a definition of average speed rather than like what we can see down here is there's instantaneous speed. We'll get into that in a second. But average speed is distance over time. In other words, you can think of it as just being a simple ratio, but it kind of explains, like if I say, hey, I'm in my car going 30 miles per hour, 30 miles per hour is a speed. And if I maintain that speed for a motion process I'm describing, in other words, maybe I'm going from one place to another or just going down the block and I continue to travel at 30 miles per hour, I can also claim that that's my average speed. But really, let's say I actually went 30 miles in 1 hour, that'd be an interpretation of how I got that number. Although, I could also say I've gone 15 miles in, say, a half hour. That would also be an average of 30 miles per hour, right? So that's kind of a little bit how that works. Now, velocity, though, maybe gets a little bit more complicated. So maybe I should have put speed first here. But velocity is often used in physics and is displacement over time. And as we saw, displacement is a vector and includes direction. And kind of parallel to the way speed is defined, average velocity is defined to be displacement divided by time. But that means average velocity and velocity, again, have a direction. Now, one of the issues that kind of comes up here is it's easy to define things like average velocity and average speed. But maybe what we're really interested in is instantaneous speed and or instantaneous velocity. And it turns out if somebody says my speed is whatever, usually you assume, like if I say my speed is 30 miles per hour, usually you assume that they're saying that for a particular instant in time. You don't normally assume, oh, they're talking about an average speed if they say that. So if we just say velocity or speed as a word, either of them, we're going to generally assume that we're talking about instantaneous. But the issue with the math is those are a little bit more difficult to define, because how do you actually have like an actual displacement that is like finite in size, in other words not zero, at one instant in time? And how much time is an instant in time? In that sense, to really do instantaneous, you'd kind of have like zero displacement over zero time, or you'd have zero distance over zero time. You'd have zero divided by zero, and if you know much about math, you know that that doesn't work so well to do that. So that's why those are more difficult to define. So I've presented here a definition of instantaneous velocity is the velocity at an instant that, if it did not change, is equal or would be equal to what the average velocity would have been. In other words, if I say I'm going at 30 miles per hour north, okay, that could be a velocity because I included direction there. But if I were slowing down, my average velocity would be less than that. But if I said, hey, I'm going 30 miles per hour north and I maintain my speed and direction, I'm not turning and I'm not speeding up or slowing down, then I can claim that at the instant, I claim that velocity, that's equal to what the average velocity is if I maintain that. Now, in reality, I may not necessarily maintain that, but that at least gives me a way of understanding how instantaneous velocity as some kind of length number with units over a time number with units could make sense for describing that. I've also stated down here, instantaneous speed is the magnitude of instantaneous velocity, and I could actually write that as a formula if I wanted to and say v represents speed. In other words, my convention is going to be, and a general convention is, if you see v without a vector symbol above it, oftentimes that's going to represent speed rather than velocity. Now, I say oftentimes because if you're working in one dimension, you might actually have a v and say that it's velocity. It's a little bit nebulous. It's a little bit, it can be a little bit unclear. So usually you just got to kind of, make it clear either in some written language or if you're presenting something verbally stated to make sure that whoever's reading it understands v. Does it represent speed or velocity? Usually it's pretty contextually clear though, but it's something to be aware of. We do kind of use the same symbol, and sometimes that can be confusing. But if I write this formula here, this is saying speed is equal to magnitude of the velocity vector. So these two vertical lines here kind of look like absolute value in math. That's commonly used notation, although some people use double ones. If you've seen that in a math book, that happens. That says the magnitude of this vector, and so in that sense, this equation kind of summarizes what this line says. As a last thing that I have here, and this is maybe something we should assume that everybody knows about, the rate equation. Sometimes it's called in math textbooks. I've sometimes seen it stated as d is equal to r times t if r represents rate, but in physics, we're not going to use r for rate. when we're talking about rate of motion, we're going to be either talking about speed or velocity, and the symbol is pretty much always going to be v. So this is saying distance is equal to speed and or velocity times time. Probably speed would be better there, but in one dimension, it can be, again, be a little bit nebulous. What does that v really represent? So we're going to see that come up in examples, and we're going to also explore some of the nuances about how average velocity, average speed versus instantaneous velocity, instantaneous speed. How do those things, those quantities, how are they, what are they for different situations? Because there's definitely some subtlety there. But again, we will see that in the examples.